And welcome back. Today we're going to talk about the Cauchy Riemann equations. This is kind of a bonus lecture. It doesn't fit within the natural thread of development of calculus from first principles, but it's a really important concept about complex functions, and so I thought this would be the right time to do it. The Cauchy Riemann equations allow us to understand a function in terms of its real parts. So the complex plane is the set of all z, but z can be written as x plus I, y, and so we can think of it as R2. And if we have a function from the complex plane to the complex plane, then that function can be considered as a function of two different inputs, x and y. So if we have z equals x plus I, y, then f of z, a function of one complex variable, can be thought of as a function of two real variables, x and y. And the output of that function can also be thought of as being made out of two real variables, some real part of the function plus some imaginary part of the function. So this allows us to take one function of a complex variable and really consider it in terms of two different functions, a real valued u and a real valued v, both of which are functions of two real variables. Now, if you love real variables and you're familiar with multivariable calculus, this can be really useful. But notice that everything is doubling here. Instead of having one output, we have two functions. Instead of having one input, we have two input variables, x and y. And so this doubling adds to the complexity and isn't always the right way to think about these things, but it is a powerful way of looking at this. Now, what the Cauchy Riemann equations explore is what happens when we look at the derivative under this perspective on the function. Well, the derivative is the limit, as normally I write as w approaches z of f of w minus f of z over w minus z. But here I'm using the h definition. As h approaches 0, we're calculating the limit of f of z plus h minus f of z divided by h. And this limit is as w approaches 0. That is a w approaching 0 within the complex plane, which basically means that when we're looking at the definition of the limit, for every epsilon, there exists a delta such that for every h in the complex plane, with a distance of less than delta from 0. So that gives us a delta ball around 0 in the complex plane as the right range of sort of relevance of this h here. Now, that includes some real values of h, but it also includes some imaginary values of h. And so this limit, if it exists, must be equal to a limit where h takes on only real values. And it must also be equal to a limit in which h takes on only imaginary values. And so we can say that this limit is equal to the limit as h goes to 0, h is in the real numbers of the same, f of z plus h minus f of z over h. And it is also equal to the limit as h goes to 0. Here, I'm going to put h in the real numbers again. That might seem like I'm doing this wrong. Really, what I want to do here is I want to imagine, I want to take imaginary h, but instead of letting h be literally imaginary, I'm going to use ih instead of h in the formula where h is real. So here we get the limit of f of z plus ih minus f of z divided by ih. And notice that the ih here is a constant, which we will soon be able to factor out. Now, here, if h is real, then what we'll be able to do is we'll be able to interpret this in terms of the partial derivatives of u or v. First, let's put them in. So this is the limit as h goes to 0, h in the reals, of, well, this is u of z plus h. So what is that? This plus iv of z plus h. But those should be expressed in terms of x and y. So this is u of x plus h y plus iv of x plus h y. That's f of z plus h, right? Here's z plus h. And notice that because h is real, we only adjust the x variable. And then here we subtract u of xy, and we furthermore subtract iv of xy. Now we divide by h. This limit here is a little bit different because we're adding h to the imaginary portion of the complex number. So this limit is actually f of x y plus h. Notice that this adjusts the value of y upwards, except I want to write u here plus iv of y plus h. So here, this is the formula for f, and I have adjusted the imaginary portion up by h, because h is a real number, ih is an imaginary number, and that changes the input y. So then we get subtract f of z, which is the same thing as it was over there. We're subtracting u of xy, and we're subtracting iv of xy. So we have the limit now as h goes to zero, within the real numbers. And then, of course, we're dividing by h. Now, this limit has a u contribution here and here, but it also has a v contribution here and here. And multiplying v, we always have this imaginary number I. This u is a real valued function, v is a real valued function multiplied by I, and v is a real valued function here multiplied by I. And so this whole thing can be separated. It can be separated into the limit of u of x plus h minus x plus h comma y minus u of xy over h. That's the real part, and that's as h goes to 0 in the real numbers. And then we furthermore have plus I times the fraction, this is not working out, times the fraction v of x plus h comma y minus v of xy. So I'm separating out the real and imaginary parts and separating this fraction. And then over here, this separates in exactly the same way. This is equal to the limit as h goes to 0 of, let's separate the u's. Oh, I dropped this I, which is going to be really important here. Let's make sure this is still here. So I'm going to leave this I here for now, and then we'll deal with that later. So, well, actually, let's factor out the I immediately. So I think it'll be easier to understand if I just take that I and factor it out. So this I goes here. Now, that leaves us with basically a similar situation, except we have u of x, y plus h minus u of xy, and that divides by h. And then we have this iv and this iv. So here we have iv of x, y plus h minus I, well, let's factor out the I to here, minus v of xy. So let's just track through where everything went here. This huge limit got split up into two fractions. This I got booted to here. This I and this I got factored out to here as the multiples of the portions v. Now, once this limit is split, then what we get here is we get some partial derivatives, right? So this is by definition the partial of u with respect to x, which can be written u sub x or it can be written du dx, but the du dx is probably the more familiar notation. So this is the partial, that's a partial derivative. So this is the partial derivative of u with respect to x. This thing, similarly, is the partial derivative of v with respect to x. So that's the partial of v with respect to x. So that accounts for everything over here. Now here we have the 1 over I, so this is equal to 1 over I, times, and what else do we have here? This thing, by definition, is the partial of u with respect to y. So that's partial u with respect to y, and this thing, by definition, is the partial derivative of v with respect to y. So that's partial v, partial y. Now, this equation by itself wouldn't be worth much, but it really is very valuable when we remember that u and v are real valued functions. So u is the real part of the output f of z, and v is the imaginary part of the same, which makes u and v are both real valued functions. This is an equality among two complex numbers, this complex number here and this complex number here. but this is real and this is real. And so what we can do here is we can easily detect what is the real part of this. It's du dx, and we can easily find out what is the real part of this. It'll be even easier if I don't drop that I here, which comes from here. So let's figure out what is the real part of each side and equate them. Let's figure out what's the imaginary part of each side and equate them. And then we'll see what happens. So I think I'm going to take the right-hand side of the board here. Make sure that you have a good frame. You can pause first. So from these equations, we can equate real and imaginary parts. And so the real part here is du dx, du dx. And the real part over here, well, you just multiply the I through, you get something imaginary here, and you get dv dy. So du dx is equal to dv dy. Now, this is already kind of shocking, right? U was the real part of f of z, and v was the imaginary part of f of z. These looked like they were independent functions of x and y separately, but here you get a weird interrelationship between them, that the derivative of u with respect to x and the derivative of v with respect to y are equal. And I've written this somewhat sloppily using d's. To be perfectly precise, I should write partial derivatives here. So the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y. Now, okay, so that's obtained by equating the real parts, which come from these terms. Let's equate the imaginary parts. So we get also the imaginary part of this is dv dx, which is supposed to be a partial. So dv dx, partial derivative here. What's the imaginary part of this? Well, this is 1 over I, but 1 over I is the same as minus I. And so read this as minus I times du dy, and then the imaginary part will be minus du dy. So that's minus du dy. And so we get these two equations relating the partial derivatives of u and v. And these equations are called the Cauchy Riemann equations. They have to be true for any differentiable function from the complex numbers to the complex numbers. This can help. One of the uses of this, one of the simplest, straightforward early uses of this is you can very easily prove that a function from the complex numbers to the complex numbers is not differentiable by checking whether the Cauchy Riemann equations are true. If they are not true, then the function is not differentiable. One way that this can be really easy is if you have a function like the modulus of a complex variable. If you have a function like the modulus of the function, then you can figure out what is the u and what is the v, and it turns out that the du dx will end up being non-zero, but the imaginary, that's a real valued function, so the imaginary part of that function is uniformly zero. So v is just a constant zero function, so dv dy will be zero. So you can say, well, this is not going to be zero, but this will be zero, and therefore the function can't possibly be differentiable because it doesn't satisfy the Cauchy Riemann equations. Another thing we can do with the Cauchy Riemann equations is we can apply them essentially twice here. Notice that if the function f prime, so if the function f is differentiable, then we get the function f prime. And if f prime itself is differentiable, then we can apply the Cauchy Riemann equations to its derivative. Now notice that its derivative is staring at us right here, right? Because these were all equal to the derivative. I erased the right-hand side, but this was all a calculation of the derivative of f. If the derivative itself is differentiable, then not only do u and v satisfy the Cauchy Riemann equations, but du dx and dv dx also have to satisfy the Cauchy Riemann equations. And that's kind of interesting because that means that we get second derivative information. That is, provided that f prime prime exists. So let's write out what happens here. If f prime prime exists, then we get then du, so the partial of u with respect to x and the partial of v with respect to x now satisfy the Cauchy Riemann equations. And so we get second partials. We take the partial of this with respect to x and the partial of this with respect to y, and they must be equal. So the partial squared of u with respect to x squared is equal to this thing partial with respect to y. So that's partial squared v with respect to y with respect to x. So that's interesting, but maybe not interesting enough yet because it's a strange kind of relationship between a mixed partial of v and a partial of u. But the real and imaginary parts of this thing, which is an alternate expression for the derivative that we calculated, must also obey the Cauchy Riemann equations. So let's write this in terms of its real and imaginary part. This thing actually has a real part, which is dv dy, right? Multiply the I in and you'll get the real part dv dy, and an imaginary part, which is minus du dy. And so dv dy and minus du dy must also satisfy the Cauchy Riemann equations. So let's write that. That's, whoops. So if we write that, then we get the partial with respect to x of this thing, according to that, must equal the partial with respect to y of that thing. So is that what I want? Yeah. So we're going to get the partial. This is no good, so I'll have to get this one. So we're going to get the partial with respect to partial squared, partial x, partial y of v. So what I'm doing here is I'm applying the Cauchy Riemann equation to this information to tell me about v, and then that's equal to the partial with respect to y of the imaginary part, which is du dy. So that's the partial u partial y squared. So, and then that has a negative sign on it. So I'll put the negative sign here. So that's interesting. This thing, du dx squared, d squared u dx squared, is equal to this mixed partial of v, but for a completely different reason, the same mixed partial of v is equal to this. And so if we take these two equations, then we can combine them to say that this thing, which is entirely about u, is equal to this thing, which is also entirely about u. And so we get partial u partial x squared equals minus partial squared u partial y squared, which is kind of surprising. And then this is called the Laplace equation, and we usually write it partial squared, well, there are lots of ways of writing it, but partial squared partial x squared plus partial squared partial y squared u equals 0, right? Move this term to the other side. And then think of this as a second order differential operator, and that second order differential operator operates on u and yields 0. So, so that's another perspective on what we get from the Cauchy Riemann equations. Now, I did this only one way. There's another way to do this. Notice that I neglected this. I applied this to both sides of the first derivative. I did not apply this to both sides of the second derivative. If you take that latter route, then you also get the same differential operator operating on v yields 0. So there's a second order differential operator that operating on the real part of a complex function always yields 0, and same thing for the imaginary part of that function. And we have a name for functions of two variables that obey this operator, that obey this equation. We call them harmonic. So this demonstrates that the real part of a complex function is a real valued function which is harmonic, and the imaginary part of the complex function is also a real function which is also harmonic. And so this is some interesting derivative calculations that all stem from the existence of this limit. and the fact that h could be real or imaginary in this limit.